Okay, we have one more word problem to go over here. So a ball is thrown upward from a roof of a 100 feet building with an initial velocity of 20 feet per second. The height of the ball in feet can be modeled by h of x equals negative 16 x squared. Now, what do we know about the parabola? If I start with a negative 16, that means my parabola is going to open downward, okay, plus 20x plus 100. What's the y-intercept? Can you see the y-intercept right away? What is it? Yes, 0, 100. Okay, where x is in seconds, where appropriate, round answers to 3 places after the decimal. Okay, so all of those little details are important because that's where we want to round to. Also, if we're talking about rounding to decimal places, it probably means we're going to be using the quadratic formula. Just a little hint, maybe. It's a good idea. Okay, so what are the units for the x-axis? Seconds. And what are the units for the y-axis? Height in feet. Actually, I should say this is time in seconds. So if we wanted to go ahead and label this down here, time in seconds, and here's the height in feet, and you already said that the y-intercept is 0, 100. So we might as well label that 0, 100, plot it and label it, okay? Now I'm going to scroll back up. Algebraically determine when the ball reaches its maximum height. So what's going to happen is you throw the ball, it goes up, and then it comes back down. It's going to make a parabola shape. So its maximum height refers to the vertex. Good. Code for vertex. How do we find the vertex? X equals negative b over 2a. If we come back to our equation, tell me what a is equal to. And b is, and c is. Good. Okay, so we're going to plug that in. I have negative 20 divided by negative 16 times 2. Sorry, I just did that backwards. That's a commutative property, though. That doesn't matter, right? So here we have negative divided by negative is a positive, so 20 over 32. And let's make it into a decimal. So 20 divided by 32 equals 0.625, or you could reduce the fraction either way. Okay, so algebraically to determine when, and then we of course want to answer it in a sentence. After 0.625 seconds, the ball is at a maximum height, and we want to actually find out what that maximum height is. So how do we find the maximum height if we know when it's reaching the maximum height? Exactly, we want to plug it in. So we take our equation and we're going to go h of 0.625 equals negative 16 times 0.625 squared plus 20 times 0.625 plus 100. So again, I'm going to use the calculator for that. Negative 16 times 0.625. By the way, I changed it back into a fraction. We could also use the fraction 5/8. Actually, it might even be a little easier to type in because apparently I don't know where to put the decimal point. 625. Okay, we're going to square that plus 20 times 0.625 plus 100. So the maximum height is 106.25. 106.25, and the units are feet. Okay, maximum height, and you can put it into your sentence of 106.25 feet. Okay, algebraically determine, and by the way, you're going to be plotting those. You know you're going to be plotting them, so you might as well kind of come back here. 5/8. Where is 5/8? 5/8 is a little more than half, 0.62. All right, and then, so it's somewhere around like here. I'm going to write it as 5/8 just for fun. And 106.25. Okay, so that's the vertex. Maximum is code for vertex. Algebraically determine the time it takes to hit the ground. How do we find out when it hits the ground? Well, we want to solve h of x equals 0. Essentially, that means we want to take the equation and we want to set the equation equal to 0 because that means the height is 0, and we want to solve for x, which is the time. So I'm writing the equation, I'm setting it equal to 0. Last time when we were factoring these, we were able to divide everything by the greatest common factor. Remember that once you set it equal to 0, you can divide out that negative. Pretty sure this is not going to factor, but we can always try. So what is the greatest common factor? Because remember, when you divide out the greatest common factor, you're going to be working with smaller numbers. So the greatest common factor, does anybody know what it would be? 4. And we can divide everything by a -4. We're not changing the equation. I mean, we're changing the equation, but we're not changing the actual equation of the parabola. We're just, because we're solving and we can do whatever we want so long as we do it to both sides, that's why that's a legal move, okay? Minus 5x minus what? 25, yeah. Okay. I was just checking, see if you're paying attention. All right. Now, do you want to try and factor that? You have to use the AC method. So 4 times -25 is -100. Can you think of two numbers that multiply to -100? That add to -5? I'll let you think about it for a second. Probably not, because I don't think it's factorable. Okay, because that's why we want to round. So if it's not factorable, then what are we going to use? Yes, we can't use the square root method, so we want to identify A, B, and C. So I'm going to use a different color. A is equal to 4, B is equal to -5, C is equal to -25. So we're going to go x equals -b. What's -b? +5 plus or minus the square root b squared, which is 25, minus 4 times A times C, all over 2 times A, which is 2 times 4. 5 plus or minus the square root of 25. And then what's all that? 8 times 25, isn't that 200 plus 200? Am I right? Or maybe this was factorable, actually. Are you guys paying attention? Am I doing this right? Oh, no, that's 16. Sorry, 16 times 25. What is 16 times 25? 400. So plus 400 over 8 equals 5 plus or minus the square root of 425 over 8. Is 425 a perfect square? I don't think it is, but let's try it out. 5 plus the square root of 425 equals not a perfect square. Divided by 8. So one of our answers is 3 point. How many decimal places should we round to? Does anybody remember what it said? Yes, so 202 seconds. And then the other one would be 5 minus the square root of 425, and then divide that by 8. And that gives us negative 1.952 rounded to 3 decimal places. And that's how many seconds. So which answer would you use here? Only the positive, because we don't care about a negative time. We're not going back in time, so we can't have negative time. Okay, so it went up to the vertex, and then it went down about 3.2, which I'm going to estimate to be around there. So it went up, reached its maximum height, and then the ball fell down. Of course, you could do a much nicer job if you plug it into your calculator and get a few points to plot here. But we're just graphing the function and labeling the information we found. So we have the vertex, we have the y-intercept. Here, 3.202, 0, that's when the ball hits the ground. Interpret your results in a complete sentence. The ball hits the ground after 3.202 seconds. Don't you love how I'm writing over my other writing? Okay. In the context of the story problem, state the domain. So now the domain of the equation of the graph itself is different than in the context. In the context, remember, we could also draw like dotted lines. There's more to the parabola than we see, but we only care about the positive section when the ball is above the ground. We don't care when it, slices into the ground and then heads down to China. We don't care about that. We only care about all this positive time. We don't care about a negative x-intercept. So what would be the domain in the context, meaning the x values that would make sense? 0, 2? Yes, and we could include both of those, and therefore we would use the bracket to show that the numbers are included. What about the range? The range is from the smallest to largest. So what's the smallest y value? Also 0, and we include it. And what's the largest y value? Yep, there it is. Okay.